Hey guys, today we're going to talk about conservation of momentum. In a closed system, momentum always has to have the same total value. While different objects can be moving at different rates, the sum of all of the momentums have to be the same. So, momentum is a vector quantity. This means you have to include both magnitude as well as direction of the motion. If the system is a closed system, just like mass and energy, momentum is always conserved. That means if you have a total of 100 units of momentum, you can have it split 50-50 between two items, you can have it split 75-25. It doesn't matter as long as they both always add up to 100 total units. So momentum can be transferred between objects, but the total sum must always remain the same. Since the masses will stay the same in a small collision, the only thing that should change is their velocities. So I know in big collisions you can lose parts of a car or things may fall off, but in small fender benders we're going to assume that that doesn't happen. So in the collisions that we're going to be calculating, the mass is a constant number before and after the collision. The velocity is the number that is going to be changing. So we're going to start with the basic momentum equation from the last video, and that equation is P equals m times v. Then we have to take into consideration how many objects are interacting, as well as their initial and final characteristics are. So the initial momentum has to equal the final momentum. But what if you have three things colliding? That means the initial of object 1 and the initial of object 2 and the initial of object 3 have to equal the final of object 1 plus the final of object 2 plus the final of object 3. So this equation can be used for as many items as we possibly need, but most of the time I'm not going to tell you the momentum is 50 kilograms times meters per second. I'm going to give you their masses and their velocities. So what we're going to end up doing is simplifying this out even more. So mass of object 1 times the initial velocity of 1 plus mass of the object 2 times the initial velocity 2 plus ... That's going to tell me I can have as many of these setups as I need. Final of object 1 plus m2 times final velocity of object 2 plus ... So if we have 6 items in the beginning, we have to have 6 items at the end. So that ... means you're not limited to 2, you can have as many as you need. So notice, I've just taken m times v from this original equation. I've added a number here for the mass of each individual object, and I've added a number and a letter here to tell me what the velocity of each individual object is, as well as if it is the initial velocity or the final velocity. So this bottom equation, this is going to be your go-to. This is what we're going to be using for the rest of this unit to help us calculate different unknown variables. So practice example number 1. 2 lab carts are pushed together with a spring mechanism compressed between them. Upon release, a 5 kilogram cart repels in one direction with a velocity of 0.12 meters per second. The 2 kilogram cart goes in the opposite direction. What is the velocity of the 2 kilogram cart? So if I draw a picture, this is our 5 kilogram cart, and this is our 2 kilogram cart. We have them together with a spring in the center. The 5 kilogram cart travels this direction, and the 2 kilogram cart travels in that direction. So I'm going to list my knowns and unknowns. Mass 1 is 5 kgs. Initial velocity 1 is actually 0 because we are starting at rest. Mass 2 is 2 kgs, and initial velocity 2 is 0. Now I need to know the final velocity for object 1 and the final velocity for object 2. Final velocity for object 1 is 0.12 meters per second. But if we look at this picture, in a number line, this direction is negative, so I'm going to add a negative sign there. Velocity of object 2 is our big fat question mark. So we're going to use that equation from the last slide. m1 vi1 plus m2 vi2 equals m1 vf1 plus m2 vf2. And we have 5 times 0 plus 2 times 0 equals 5 times negative 0.12 plus 2 times our unknown variable. So on the left, everything equals 0. 5 times 0.12, 5 times negative 0.12 is negative 0.6 plus 2 VF2. Now before we can solve for VF2, we have to get this section by itself. So we're going to add 0.6 to both sides. So 0.6 equals 2 VF2. Now we can divide both sides by 2, and VF of object 2, or the final velocity of object 2, is 0.3 meters per second to the right. Based on our diagram, this one is traveling this way, which is to the right or positive. One more practice problem. A 35-gram bullet strikes a 5-kilogram stationary piece of wood and embeds itself into the wood. The piece of lumber and bullet fly off together at 8.6 meters per second. What is the original speed of the bullet? So I'm going to list our knowns and unknowns. M1, VI1, M2, VI2, VF1, and VF2. Mass 1, the bullet. Notice my bullet is given in terms of grams. We do want to switch that to kilograms. So that's 0.035 kgs. The initial velocity, we don't know. M2 is 5 kgs, and the initial velocity is 0. And then we have final velocity 1 and final velocity 2. Both of these happen to be the same number because those two objects are sticking together in order to travel off on their own. So what I'm going to do with my equation is adjust it a little bit. I have m1 vi1 plus m2 vi2. Since these are separate before the collision, I am keeping them separate in my equation. But the piece of wood and the bullet embed themselves together before they fly off. So for the second part of the equation, I'm actually going to add my masses first, then multiply by my final velocity, since both of these velocities are exactly the same. I'm allowed to do that because the velocities are the same. So m1 vi1, we have 0.035 times vi1, which we don't know, plus 0, because vi2 was 0, equals 0.035 plus 5 times 8.6. So 0.035 vi1 equals 43.3, and I have to divide out by 0.035, and VI1 has a value of 1,237.17 meters per second. So that bullet was traveling pretty quickly to be able to embed itself in the piece of wood and have them travel off at 8.6 meters per second together. So in class tomorrow, I'm going to give you some examples of how to go through and calculate this. You might have things starting together and separating. You might have things starting separate and then ending together. But either way, you are going to use some version of this M1 VI1, M2 VI2 equation in order to solve for an unknown variable. So I'll see you tomorrow so we can practice.